In this short lesson, we'll see the concept of a norm and how it relates to calculating distance. You're probably familiar with the traditional straight line or Euclidean distance measure. Given 2 points x and y with coordinates x1, x2, and y1, y2, the distance between them is the square root of x1 minus y1 squared plus x2 minus y2 squared. A second common distance metric is rectilinear distance, the absolute value of x1 minus y1 plus the absolute value of x2 minus y2. This sort of distance is sometimes used, for example, when driving in a city where streets are laid out as a grid, which is why it's sometimes also called the Manhattan distance. We can generalize both of these to be the absolute value of x1 minus y1 to the pth power plus the absolute value of x2 minus y2 to the pth power and take the pth root of that sum, where p would be 2 for straight line distance and p would be 1 for rectilinear distance. And if we happen to be in a space with more dimensions, let's say n dimensions, we can write this as the sum over all n dimensions of xi minus yi absolute value to the pth power and the pth root of all that sum. This formula is known as the p-norm distance. For example, the 1 norm distance, the 2 norm distance, etc. It's also called the Minkowski distance of order p. In theory, we could choose other values of p also. P equals 3, p equals 10, p equals 1,000, or anything else. But surprisingly, the third most common value of p that people use is actually infinity, the infinity norm distance. Anytime I talk about infinity with people who don't use math for a living, I can see their eyes start to glaze over. But in this case, it has a meaning that's actually pretty easy to understand. Here's the formula with infinity substituted for p. Now, technically, we should probably refer to it as the limit as p goes to infinity of this, but let's ignore that. And a quick warning for all of you who like formal mathematics, I'm going to be very informal with my infinities in this discussion because it's easier to get a good intuition that way. So let's write out the sum. Now, if we have n different numbers all to the infinity power, the largest one will dominate the rest. For example, 8 to the infinity swamps 7 to the infinity, and the sum of those two is so close to 8 to the infinity that 7 to the infinity is irrelevant. So this sum is just about equal to the largest among the differences in each dimension, to the infinity power. Now let's simplify. We have the infinitieth root of the infinitieth power of the largest difference. The root and the power are the same, so they cancel, and we're left with just the largest difference. And that's all the infinity norm is, the largest of a set of numbers in absolute value. If you're thinking that the phrase infinity norm sounds like it should mean something a lot more complicated, join the club. The first time I heard it was in a casual conversation with a friend, and I was really impressed with him until I sat down and worked out the math and realized he just meant the biggest. At this point, you might be wondering two things. First, what kind of person has friends who say infinity norm in casual conversation? I know, I have some friends who are pretty nerdy, but this guy would say I'm pretty nerdy too, so I guess it's a good match and a good thing we both work in analytics. Second, why would anyone ever use the infinity norm as a distance measure? Here's just one example. Think about a warehouse that has an automated storage and retrieval system. In each aisle, there's a machine that moves up and down the aisle to the right place, and also stretches up and down vertically to reach the right height. Suppose we tell it to pick this item right here. It might move along the aisle to the right place, and then stop and stretch up to the right height. If so, then the total time it takes before it can pick the item is the along the aisle time plus the up and down time, the exact definition of a 1 norm. But suppose the machine was designed in a smarter way. As it's moving down the aisle, it's simultaneously stretching up and down to the right height. How long does it take from when it starts moving until it's ready to pick the order? Whichever takes longer, moving or stretching. If it gets to the right place along the aisle before it finishes stretching, then the stretch time is how long it takes to be ready. And if it stretches to the right height before it gets to the right place in the aisle, then the along the aisle time is how long it takes to be ready. Either way, it's the larger of the two times, and that's exactly the infinity norm of the two. So now you're part of the club too. And the next time you're waiting in the slowest checkout line at the supermarket or stuck in highway traffic when all the other lanes are moving and yours isn't, Don't be afraid to complain about infinity norms.